Judy, I don't understand the relationship between a p-value and alpha. Thank you for telling me. I got you. I will explain that in just a second here. All right, so I'll jump into some statistics content. If you have any questions, just throw them up in the chat and I'll try to answer them along the way. If I don't answer your question, just ask it again because maybe I missed it. I apologize. All right, so let's go down to, where's all my paper? Here we go. Let's go down to this mode. Boom. And let me lower my boom. Zoom. Zoom. All right. Yeah, this I love having this tripod set up here. This thing seems to work great. All right. All right. Judy, let me try to explain p-values and alpha. All right. So I'm going to write down something really clear. Hopefully this, like the basics. Ooh, other people are asking stuff too. There's something about the Department of Education. Sorry. All right. I was just sorry. I was just getting caught up on the chat. But anyway, statistics stuff. Let's see here. Let's think p-value and alpha. Right. Let me give you the most essential basic of it, right? That when we have a significance test, we'll frequently use a normal distribution. Later on, we'll use t-distributions or even chi-square distributions to try to decide, to calculate a particular p-value. The alpha that we come up with, right? So let's say we had a right-tailed test. It was right-tailed. And we had an alpha that was 0.05, right? Then what we could do is we would just shade everything on the right of our distribution. In this case, it looked like I've got basically a normal curve. And we'll shade everything to the right. You can imagine that would be, say, 5%, right? So I just shaded in the right tail that's 5% of the normal curve. Now, interestingly, we know how far out you'd have to go to get to 5% in terms of standard deviations, right? To get to 5%, you'd have to go 1.645 standard deviations above the mean, at least in the standard normal distribution, right? So, and I know that because I just memorized a bunch of stuff that has to do with z-scores and levels of confidence and all that kind of junk. But so that's that. Now, when we calculate a p-value, we'll be calculating everything to the right as well. And the key most basic fact about p-values is that that if the p-value is less than alpha, then you reject the null hypothesis, right? And then the obvious other result would be if the p-value is greater than alpha, then you fail to reject HO, right? So if the p-value is less than, then you reject. In a curve like this, if we got a z-score for our sample thing, like so our test statistic, let's say our test statistic ended up being something like over here, right? Then the p-value might be just this little bit of area right there. I've spelling p-value wrong. P-value. Then the p-value could be like just this little bit of area there. And now if I calculated what that was using normal CDF, then this would be less than 5%. Let's say the z-score that we got was something more like 2.1, right? Then the p-value at 2.1 is going to end up having an area under the curve here that's less than 5%. So that would mean I reject the null hypothesis, right? And if I wanted to know exactly what it was, I could just go normal CDF. I could say like 2.1 to infinity, 0, 1, paste, and Shazam. That was 1.78. And so again, this is just a quick made up example, but this p-value would be 0.0178. And since that is less than 5%, I would reject the null hypothesis, right? However, right, let's say in this right-tailed test that we had a test statistic that was something like, let's say, so this would, let's say z equals 1.48, right? And then 1.48 would be something like right there, right? So let's say this is our new test statistic z. And if I was to do a right-tailed test, then I would shade everything to the right, right? And now you can see that this p-value is, you can see visually, is going to be bigger than 5%. And so I'm going to fail to reject. Now, exactly how much bigger than p-value is, how much bigger is it? Well, let's see. If I did normal CDF and I did 1.48 to infinity, and now that's like 6.9% sod, no laughing. All right. My gosh. 0.069. And so in this case, I would fail to reject because this p-value is going to be bigger than my level of significance. And so, Kira, I see you ask, what did you ask? So a p-value is an area under the curve. Yes, the p-value, it's a probability. And usually the way that we're calculating p-values is by using normal curves. And in normal curves, the probability has to do with the area under the curve. So yes, the p-value, based on the way we typically calculate them, will be based on some area underneath the curve. Sometimes though, actually yesterday at the end of our discussion, or if you remember, we were talking about p-values and we even used the binomial distribution to calculate a p-value. I'll tell you that's not standard. This is not standard in AP Stat. It's not standard in AP Stat, but it's absolutely valid because all a p-value is just a probability, right? A p-value is a probability. It's the probability of something happening, probability, right? And what kind of probability is it? Ooh, let me take out my paper again. This guy from a video. It's the probability that a statistic will take a value at least as extreme in the direction of the alternative hypothesis as the one we observed given the null hypothesis is true. It's a conditional probability that assumes the null hypothesis is true, right? But it is in fact a probability, and it will always involve shading everything to the right, or shading when it's a right-tailed test, shading everything to the left when it's a left-tailed test, or using symmetry like we saw for several two-tailed tests. So Judy, is that sufficient explanation for you? Do you still have questions about p-values and alphas? Oh, great, Judy, I'm glad. That makes me happy. Anyone have any other questions about statistical stuff that I could try to answer now? I'm ready to answer your questions. Good morning, Harry. Welcome. Glad you could join us. Other questions about p-values, levels of significance, etc. All right, I'm not seeing any more questions. So let me, and I'm still patient. You can still ask questions. Let me just ask, did you guys, yes or no, did you guys look at the videos and start looking at the stuff about errors in significance testing yet? Where we talk about a type 1 error and a type 2 error. Yes or no, did you start to look at that? Or did, all right, so Kira, you're going to look at that today. That's fine. See lots of yeses, lots and lots of yeses, yeses. Yeses make me happy. Amy's going to do it today. That's totally fine. I might, for people that haven't done it yet, I might just start to introduce you to the idea anyways right now. People that have, do you have any questions about it? Or I'll say in general, I found that in the past, students have had a real tough time with type 1 and type 2 errors, especially when you're asked to write out what a type 1 and a type 2 error would be, and its consequences. It can be a tricky thing. Do you have any questions about it, or do you? Otherwise, I'm just going to start asking you questions about type 1 and type 2 errors just to see what you guys know and remember about it. All right, let's see. I'm just going to start doing stuff. All right, let's just talk about type 1, type 2 errors. Let's think about, let's go back. I don't think I used this in the video or not. Remember when we had our friend and we were talking about, I'll just draw stuff. Remember when we used the example several times of the friend who was thought he had a die that was an unfair die. And so we has a null hypothesis that the probability that he could roll a, what am I even doing? What am I doing? We had a null hypothesis that your friend had a fair die, and so his probability of rolling a 6 was 1/6, and the alternative was that he had a better than 1/6 chance. And then we ended up getting a p-hat that was 19 out of 80, and from that p-hat, we ended up with a p-value that was which was equal to the probability of getting a p-hat greater than 19/80ths. And I remember that the answer was something like 4.6% for a p-value, right? And therefore, since our p-value is 4.6%, we said something like we reject the null hypothesis since the p-value of 0.046, say less than alpha equals 0.05, right? That the p-value was less than our level of significance, so we rejected the null hypothesis, and that meant that we do have significant evidence that that your friend has an unfair die, essentially, right? Not only unfair, but in fact unfair to the advantage of rolling 6s, right? So we did have significant evidence of that. So my question for you guys is, since we rejected the null hypothesis here, does that mean that he definitely does have an unfair die? I mean, we saw that we had significant evidence that caused us to reject the null hypothesis. Remember that the ultimately null hypothesis is that this is a fair die, and the alternative is that it's a kind of unfair die. Is this the reason that, so we reject a null hypothesis? Does that guarantee that this is in fact an unfair die? And I see people starting to answer. I see lots of people saying, no, you are correct. Just because I found significant evidence that it is an unfair die, it doesn't mean that it actually isn't a fair die. It's possible that just by chance, our friend could have managed to roll a die an unusually rolled a 6 an unusually large number of times, even when it was a fair die, right? And so there is a chance that we made an error. Right, an error. We can make errors when we do significance tests. All right, Liam, I like your little I don't know thing. That's pretty cute. Josephine, I see you asking, how did we get 4.6%? I can quickly recap that with you. That we actually I'm just doing it from memory. We actually calculated it in the video online, and you can look at that to see how it's done, but I'd be happy to recap it with you in a little bit. But so the whole point though right now is that we could have made an error when we rejected the null hypothesis. So my friends, let's say that in reality, the die is fair. It actually really was a fair die. What kind of error did we make? Was it a type 1 error or was it a type 2 error? Type 1, is it type 1 or type 2? Let's see, what do you guys say? Let's see, I see people starting to respond. It would be, let's see, I have 4 people, 5 people, 6 people. All right, I'll wait for a couple more. Does that say unio, Harry? Did you mean uno? I think you meant uno. Very good. Yes, this would be, if it is in fact a fair die, and we made an error because we said it's not fair when it in fact is fair, that would have been a type 1 error, right? And a type 1 error is what we call anytime we reject the null hypothesis when we should not have rejected the null hypothesis, right? Now, can anyone tell me what was the probability that we make a type 1 error in this particular scenario? What was our probability of making a type 1 error, right? Let's see here. I see some answers coming in. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. Dun, 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 dun. And I see only 2 people answered, and they both said 5%. Oh, now we've got 3. Doreen is chiming in. She says 5% as well too, and the answer is 5%. Right? There was a 5% chance of us making a type 1 error here. Who can tell me why there was a 5% chance of us making this type 1 error? Why was it 5%? That's such like a specific number. Why 5%? Kate makes it very clear. Noah does as well too, because alpha represents the chance of making a type 1 error. It's because our alpha was 5%, right? And that's, for us, this is important. The alpha that we pick, right? This is what, if you haven't watched the videos, you're going to learn that over the course of the 2 or 3 videos that I made. You're going to learn that the alpha is the probability of making a type 1 error, right? And so the way to avoid making a type 1 error is to make our alpha an even smaller number, right? The real question is, how nervous are we about making errors in this situation, right? Well, the reason why alpha is the probability of a type 1 error is because its alpha is the boundary for how extreme we would need to get a p-value, how small our p-value has to be for us to reject. And so if alpha is 5%, that would mean 5% of the time, just by chance, I could get a p-value that will be below alpha. Why? Because say I was to draw the distribution, right? There's my normal curve again, boom, and say that we just do it all standardized, n0, 1, right? Then remember our boundary at 5% significance, right? This is 0.05. Then there's a 5% chance, just by sheer luck, I could end up finding a test statistic that's out this way, right? If this represents what would happen ultimately on average, this would be my average value. 5% of the time, I could end up getting something over here just by sheer chance. So we have to accept the fact that our boundary for a p-value changes the chances of us making a mistake, right? And we always have to accept the fact that we can and will make mistakes when we do significance tests, and we have to be ready to think about that, right? If we wanted to make it harder to make a mistake, then what we would have to do is lower our alpha, right? So if we wanted our type 1 error probability to be lower, then say I only wanted a 1% chance of making a type 1 error, because I really, 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 really wanted to avoid a type 1 error, then what I would do is have another normal distribution, right? But now I'd only shade in what's over here at 1%, right? And actually 1% might be something, if I shaded that in, that's 1%. Actually, the z-score for that would be like 2.326. This guy was 1.645. This guy would end up being 2.326. And actually, I knew it's 2.326 because if I had 1% here, then I'd have 1% on this edge over there, which would leave 98% in the middle. And I have memorized that would be 98% there. So the key idea, though, is that now this particular p-value, so recall in this example that our p-value was 4.6%, which was based on, I forget the test digits. Actually, let me calculate just what that was again. And this actually will help Josephine see where we got the p-value. If I did 19 divided by 80 minus 1 divided by 6, we had that. And then we divided that by the standard deviation formula. That would be 1 divided by 6 times 5 divided by 6 divided by 80, because there was 80 trials. That's right, we got 1.7. So here, the test statistic was like 1.7, and that's why we got a p-value that was just a little bit less than 5%. It was 0.046. But now, if I did 1.7, right, just the same distance, 1.7, and this p-value is going to be 4.6%, we're going to see now, would I still reject the null hypothesis? What would I have done here? If at 1% significance, do I reject or do I fail to reject? Noah, you're killing me. Noah, never accept a hoe. Ever. Never, ever, Noah, accept a hoe. Yes, thank you, Noah. Stand corrected, right? But now, and I like how people, I see everyone else is correctly saying, fail to reject the null hypothesis. We never accept it, but now we would fail to reject it, right? Because at 1% level of significance, the p-value is, yes, the John. Now the p-value, right, which if I was to shade in, is way more than my level of significance. And so now I would fail to reject. Now, here's the downside. When I fail to reject, there's a possibility that I made a mistake again. Do you agree? Now, I made it harder to reject the null hypothesis. I said, the only way I'm going to reject that this is a fair die is if I have evidence that's significant at the 1% level, right? I made it very, very difficult to reject, so I failed to reject. But now I might still have made an error. Let's suppose it turned out that the die is unfair. That the die really, really, really is unfair, right? Then what kind of error might I have made here when I failed to reject the null hypothesis? I see answers coming in. I see the answers. I see 1, 2, 3, 4 answers. I'll wait for one more. Aaron coming in. Yes, this now could potentially be what we'll call a type 2 error, right? And a type 2 error occurs when you fail to reject it. Let me rephrase that. The type 2 error doesn't definitely occur when you fail to reject, because hopefully most of the time we don't make errors. Hopefully most of the time we're right. However, when we fail to reject, there is a possibility that we might have made a type 2 error, because it might turn out that this die really, really was an unfair die. We just didn't get enough evidence to prove it to me in this instance, right? And so In order to really be convinced by it, we required stronger evidence, but that sometimes leads us to also make mistakes, right? So in this case, what would be the consequence of a type 1 error, or excuse me, in a type 2 error here? Well, our friend really did get this unfair die, but we don't believe him, so maybe he feels bad about his purchase. He's like, oh man, I spent this money to get this great unfair die, and now you're trying to tell me it's just a regular fair die? Well, maybe I got ripped off, right? Which wasn't necessarily the case. What would be the consequence of a type 1 error? Let's go back to the situation where we rejected the null hypothesis. Well, what would be a consequence of a type 1 error? In this type 1 error, we rejected the null hypothesis when in fact the die was a fair die, right? And so that would mean your friend thinks he's got an unfair die, which gives him an advantage, but he really has no advantage, right? You might say refuse to play games with this guy because you think he's got an unfair die, but in reality, his die was actually just as fair as anybody else's. In this situation, I don't know that either kind of error would be more worrisome to me. I don't think it's more worrisome to think you have a fair die when you don't. Think you have an unfair die when you don't. That would be a type 1 error. Or think you have a fair die when it's in fact unfair. That would be a type 2 error. Either way, I don't think is necessarily that deep. So I might just think a 5% level of significance would be a fine way of trying to evaluate this situation. Tran, let's see. He going to start gambling with the other type and lose money. You think in a type 1? That's true. For your friend, that might be problematic because he's going to think that his die is an unfair die that gives him an advantage, and when it's really just a fair one. And so for him, that might hurt him because he's going to start like, oh yeah, he's going to start taking all sorts of bets that end up proving foolish because he doesn't actually have the advantage he thinks he does. I'm with you there, Tran. From his perspective, your friend's perspective, he'd probably be more worried about a type 1 error because he could start losing money. All right. 2 quick questions. So Anthony, if your alpha was 0.05 for a right tail test, does that mean it's 0.1 for a 2-tail test? Not necessarily. Okay. So let me clarify that for Anthony. Anthony, you said if your alpha is 0.5 for a right tail test, does that mean it's 0.1 for a 2-tail test? Actually, what gets doubled is not necessarily alpha. What would get doubled is, say, the p-value. So for instance, when we had a p-value of 4.6%, right? That p-value was based on a right-tailed alternative, which is because our alternative hypothesis was p is greater than 1/6. If we change this to a 2-tail test, then that changes the p-value, because then we could say that p is not equal to 1/6 would be the alternative. And if p all of a sudden is not equal to 1/6 is the alternative, then to calculate my p-value, the p-value gets doubled. Because what I would do is I'd say, okay, here's positive 1.7. Then I'd go over here symmetrically to negative 1.7, and I would shade everything this way in addition. And in this side, I would have 4.6%. And so now my p-value would be 4.6% plus 4.6%. So what's that? I could just do that. I'm just adding or times 2. That's 9.2%. So now for a 2-tail test, my p-value would be 9.2%. And that would mean that at a 5% level of significance, I would fail to reject the null hypothesis for a 2-tail test. The exact same statistic that would cause me to reject at 5% and a right tail will cause me to fail to reject at 5% for a 2-tail, right? So the level of significance can be set at whatever you want it to be, whether it's a 1-tail or a 2-tail, but the p-value doubles when it becomes a 2-tailed test, which makes it more difficult to reject the null hypothesis. Does that help, Anthony? Let's see. Let me look at what's going on here. And Noah, okay, great, Anthony. Noah, you asked the probability of getting a type 2 error is beta, and you ask a beautiful question. How do we know what beta is? Next week, you'll actually have an assignment where you'll see how to calculate beta. They'll tell you calculating beta is very, very complicated. The idea behind a type 2 error, right? In a type 2 error, then you would say what's true, the ha is true, right? That would mean in this particular instance that P is greater than 1/6. The only way to calculate the probability of a type 2 error, which is beta, would be to actually know what the ha is. We know that it's bigger than 1/6, but what is it? And so it gets, in some ways, it's almost impossible to truly know beta unless you actually know what P is. Notice in a type 1 error, you do know what P is. P is whatever the null hypothesis said. However, in a type 2, you don't know what P is because all you know is that the ha is true. You know simply that it's greater than some number, but not exactly what it is. And so it gets a little tricky. I will teach you how to calculate beta, but it is a complicated process to calculate beta. So the only thing that we could say right now is, in fact, when your alpha goes up, when it's harder to reject the null hypothesis, when it's easier to reject the null hypothesis, then beta will go down, right? If alpha goes up to like 10%, then beta goes down to a lower probability. And it's, again, I'll dig into that and show that to you another time. It's actually kind of fun to calculate. And if you can calculate it, then I think it deepens your understanding of how everything works together. But we'll look at that next week sometime. Let me see what other questions we have here. Kate, probably p-value divided by alpha. And then you said, wait, the other way around. P-value, Nakara, you said p hat minus the null hypothesis divided by the standard deviation. That is correct. Well, no, that's not what the p-value is, Kira. That's what the test statistic that we use to calculate the p-value is. So the test statistic equals p hat minus the null hypothesis divided by the standard deviation. Yeah, that's okay, Kate. No worries. All right, I hope that's helpful. Any other questions that I can answer right now? I'll pause for a second. So this type 1, type 2 error stuff, you'll see in the textbook assignments. It's mostly you trying to say what a type 1 error and a type 2 error is if you haven't done them yet. The extra worksheet that I posted for you guys to do Thursday/Friday, that has more like that, but also has some more mathy examples too. But I'll keep, even though I'll keep going back to try to talk about type 1 and type 2 errors throughout the rest of our course, because they're really, really important concepts. But they can, unless you review them a lot, it's hard to sometimes keep track about which one's which. I used to make a lot of mistakes about which one was the type 1 error and which one was the type 2 error. It probably took me a couple of years to just stop making mistakes about it. So anyway, I'm ready to help you guys think through this stuff. But all right, I don't see any more questions, so I'll still give people another minute, but I think I might cut this. We might sign out now. Definitely a quicker session than before. Yeah, you're right, Liam. I need to get my groceries, so I'm going to make sure that I get done here a little bit more quickly. Kate, you can ask it's non-stat. Really, I'm going to answer Doreen's question first. What is a test statistic? Just Z? Yeah, pretty much. The test statistic is we haven't actually formally defined the test statistic yet, and I will next week, but I'll say that the test statistic, oh my gosh, if I could only write, it's annoying myself sometimes. The test statistic equals a standard score, which is the more, can I spell standard score, which is just a z-score, right? Right. So the test statistic is always going to have a z-score formula. So for instance, it could be something like the sample mean minus mu over this guy, right? In another context, it was p hat minus the hypothesized p over the square root of p times 1 minus p over n, right? Make sure that goes all the way down. But stuff like that. This is just what I mean by a test statistic. It's just a z-score. So hopefully that answers your question, Doreen. All right, let's see here. Stock up on TP. Actually, I haven't bought any toilet paper in weeks, but I usually stock up anyways, and I think we'll be all right. You know, you don't actually, never mind. I'm not going to get into that. Not right now. When it's easier to reject the Ho beta decreases, that is exactly right, Kira. Statistic? Are you? Amalia. There you go, Amalia. Statistic. All right, Kate. I heard that the school district doesn't want teachers to reach out to students and teach them using technology in order to treat everyone equally. How will that affect us? All right, I'm glad you asked. I'll explain. Okay, so the district, I talked to McKenna about this too. Essentially, what this means is that I'm not supposed to give you grades right now. So technically speaking, if you participate or you don't participate, it shouldn't affect your grade directly, right? So like technically, you guys have a quiz on this. Only first thing that I'd actually grade is this online multiple choice quiz. And I said that you could keep doing it until you get 100. And I'm still going to have that be a policy. I'm going to record the grade that you have in Google Classroom, but I'm not going to be posting any of those grades to Infinite Campus because technically I'm not supposed to be grading you on the work that you're doing right now. So what does that mean for us? Personally, I will continue to keep track of how you guys do on stuff. And when I'm allowed to start giving you grades in the grade book, then I will reward you for what you guys have been doing here, right? And I will give you good grades for taking these quizzes and doing them, and for participating in class here. So I'll make sure that you guys get rewarded, but it's going to be sort of delayed gratification. I'll tell you from my own personal perspective, I think that the district policy is going to have to evolve because when they're saying that this is going to be 2 weeks and then we're back on the classroom, I think that's false, right? I think this is going to be going on a lot longer than that. And so eventually they're going to realize that they need a better way to deal with this in the long term. The districts, other districts around me, bold call. Are you being sarcastic, Liam? Right? This is going to go longer than 2 weeks. The other districts around us, they had a plan and they jumped right into it starting Monday, and it involves students having to turn in assignments and getting grades and all kinds of stuff. The school district of Philadelphia is very large and cumbersome and has such great variation in students and the things that they're and their resources that they have available to them, that it takes a while for them to figure out how to do things. But I suspect, like even I see Kira, you said there, that there's a good chance that we might, there's a chance that we might even spend the rest of our year learning this way. And if that's the case, we're going to have a good way to make sure that that you guys are learning and that you're rewarded for your successes. So anyways, I appreciate you guys participating. I think that, trust me, I got you guys when the quarter, I don't know when a quarter is actually going to end. I know it's supposed to end like next week or something like that. I haven't heard that that's going to get delayed, but when grades do go in for this quarter, know that I will do whatever I can to take care of you. Especially, I know some people that wanted to do some retakes, and I'll see how I can try to help people out in that situation. But I don't have any answers for that stuff just yet. But I know that I'll take care of you guys as best as I can. Things are pretty crazy, and let me see what you guys were saying here. There were some other questions. Oh, you guys are gross. But you know what? That's not really that gross. You got to do what you got to do. Then go back in like May or when it's school for the rest of the year. I agree with you, Kira. The quarter's still in if we don't come back. I have no idea, Tran. Yeah. Oh, my coffee looks good. Yeah. Thank you. This is good coffee. You know, like I have 2 ways that I make coffee these days. Here's my, this is my Bodum French press, which works great. But I also actually more often than not use a mocha cup, a mocha thingy, which is pretty cool. Yeah, this is a great mug. It's a very high quality mug that I bought from Nespresso, which is one of those fancy espresso machine companies. It's it's entirely round mug. There's no handle on it, and it just has this great little thingy like this. Anyway, it's excellent. It's the perfect size to fit coffee, and it's delicious. Yeah. Anyway, all right, guys. With that being said, hello, it's back to me again. I'm going to Harry asked if the coffee's hot. It actually is well insulated. So I've never had this, even though I put super hot coffee in, the mug itself is never super hot. It's really, really good. I like buying quality stuff ever so often. This was a good purchase. All right. So anyway, guys, I'm gonna head on out. Thank you for participating here today. Good luck doing some of the assignments. I hope you guys don't get too bored. And I'm sure you've probably gone through most of Netflix already. We'll see what happens. But I'll talk to you guys soon. And yeah, we'll be in touch. All right. See you guys. Thank you guys for saying goodbye. Goodbye to you all. Have a beautiful day. All right. I'm about to turn off the recording. Oh, Noon just joined us. Noon, welcome and goodbye. I'm sorry, but we're leaving. And but you guys can watch the recording. So okay, have a great one. Adios, my friends. Toodles. Stop the recording and